In this synoptic chemistry video, we're going to look at enthalpy change definitions. So we've covered a lot of enthalpy changes at A level. What do they all have in common? The more that we can see that they have in common, the less we're going to have to learn when we are trying to remember all of those complicated definitions. All of our enthalpy changes in chemistry are measured in kilojoules per mole. That tells us how to calculate them sometimes when we're doing it from experiment. Kilojoules divided by mole. But more importantly, for definitions, it tells us that they involve 1 mole of something. So we're always measuring an enthalpy change when 1 mole of a reactant does something, or for the formation of 1 mole of product. And when we cover the different types of reaction, we'll decide what it is that we're doing 1 mole of each time. All enthalpy changes must also have a sign, especially when we're calculating them. Positive sign for endothermic, energy in, and a negative sign if it's exothermic and energy out. And in this video, we'll also look at how we decide whether an enthalpy change is likely to be endo or exothermic. And then all of our definitions for enthalpy changes have specified conditions or states that we need to talk about. And the common ones are either standard conditions or gas state. So in this video, we'll also look at how we know whether something should be under standard conditions or whether it should be measured in a gas state. And the other thing that maybe people don't realize is that enthalpy changes will either refer to a full chemical reaction, so the kind of thing that we could measure in a laboratory, something where we could put some reactants together and measure the actual enthalpy change, or enthalpy changes can refer to individual processes, just small parts of things that happen as part of a chemical reaction, but they don't represent an entire change from reactants to products. And so that's one of the main definitions that's going to help us decide whether or not something is under standard conditions or whether it's under a gas state. So actually, when it comes to definitions for overall reactions, there are really only 4 common ones that we need to know the definitions for. So one of those is our enthalpy of formation. That is the formation of 1 mole of compound from its elements, and that's under standard conditions. For example, we could write an equation: sodium plus half a mole of Cl2 makes sodium chloride. And notice that we need, when we say standard conditions, elements are in their standard states, which means we have to think about diatomic things, and we're making 1 mole of sodium chloride, so there's no numbers in front of the NaCl. Neutralization is one we tend to maybe forget because it doesn't come up as often as formation, and that is when 1 mole of water is formed from solutions of acid and alkali, and acid and alkali solutions contain H+ and OH-. They are aqueous and they're making water, which is a liquid. So neutralization is the same equation regardless of what acids. It doesn't matter what acid and what alkali I mix, that is always the equation that I'm measuring the enthalpy change for. So these are definitely things that I could in theory measure in a lab. Formation is a little bit harder, but definitely I could do an experiment and put the reactants together and measure it. And these 2 are examples where the 1 mole is about the product formed, 1 mole of compound formed or 1 mole of water formed. Okay, what about combustion? This comes up a lot as well. This is 1 mole of substance combusts in excess oxygen or reacts completely in oxygen. Standard conditions. Again, we've got to be careful about our moles because it's 1 mole of the thing that is burning. So in this case, ethane, C2H6. And of course, the state symbols need to be in there. And then also later on, if you haven't already covered it yet, you will do enthalpy change of solution. And that is when a mole of substance dissolves in excess water. So just enough water to make sure that it completely dissolves, and that if I added any more water, there wouldn't be a further energy change. So for an example, we could do sodium chloride. We would normally just put plus AQ. We don't put plus H2O because the H2O is not really doing anything in this. And then we would just put Na plus and Cl minus and put them as aqueous ions, or it could indeed just write NaCl brackets aqueous. So these final two, again, you can see that these are things that we could measure by experiment, and you probably will have done some or will do some experiments to measure them. They are in terms of moles of substance reacted as opposed to moles of substance, a product formed. So they're talking about something happening to 1 mole of substance, it being combusted or it dissolving. What about endo or exothermic? Are there any rules that we can use for these 4 different reactions that we need to know? Well, neutralization is always exothermic, and so is combustion. Hopefully combustion should be easier to remember. What about formation? Well, you're forming compound from elements, and normally compounds are more stable than the elements they come from, which means that normally enthalpy of formation is exothermic. Not really big values like combustion, but it is exothermic. There are a few examples where it's not, and these are usually kind of unstable compounds, things that you don't see very often. When it comes to solution, definitely can be endo or exothermic, and really that's often something that you calculate using an enthalpy cycle using hydration and lattice enthalpy, which we'll cover in this video as well. So when we think of those overall reactions, that's the only 4 real reactions that we need to know, or we may have specific reactions that we need to calculate the enthalpy change for. And the thing about a reaction, a whole reaction from reactants to products, is that no matter whether it is exothermic or endothermic, it always follows this pattern of going up and then coming down. And so when we draw our enthalpy level diagrams, we always have this up, which is we often call activation energy, and then we have some energy that's given out. And that is because we always have some sort of bonds broken at the start of the reaction, and then we have new bonds that are made. Now this is quite obvious when we're looking at covalent bonds being made and broken, and we do lots of calculations for this. But actually we can consider any of those different things we looked at as being a balance between the energy in to break the bonds and the energy out. For example, in dissolving, the energy that we need to put in to break the bonds is the ionic bonds, which is the lattice enthalpy, and then the energy out is the hydration enthalpy when the ions get surrounded by water, and we'll look at both of those in a moment. So the main thing is to realize that bond breaking is always endothermic and bond making is always exothermic. And when we say bonds, we could be talking about covalent bonds, ionic bonds, metallic bonds, and we could also be talking about attractions between things. So we can think of attractions between water molecules and ions as being bonds made or broken in a chemical reaction, and we can think about attractions between electrons and the nucleus as being therefore like bonds that need to be broken or made in a chemical reaction. So let's go back and look at covalent versus ionic, because we have definitions that tell us about the strength of covalent bonds versus the strength of ionic bonds. So our mean bond enthalpy is the energy required to break 1 mole of bonds under gaseous conditions. So for a diatomic element, if I break 1 mole of chlorine molecules up, I have to break 1 mole of bonds to do that, and I will get 2 moles of chlorine atoms. Now notice that we've now changed, we're not talking about overall reactions, we're talking about individual processes that happen within a reaction, and we've now moved to gaseous conditions instead of being under standard conditions and standard states. Bond enthalpy, because of its definition, is always endothermic. Like, we define it as the energy we put in to break the bonds. But if we're doing a calculation and a covalent bond is being made instead of broken, that's when we change the sign and make it an exothermic process. Lattice enthalpy is like the equivalent of bond enthalpy, but for ionic compounds. And usually at A level, we define it as lattice enthalpy of association, putting the lattice together. So it's energy released, making bonds, when 1 mole of lattice is formed from gaseous ions. So there are a few differences here that you can see. One of the things is we're making a mole of a compound, and so there could be different numbers of ions, and we're not counting ionic bonds in the same way that when we talk about bond enthalpy, we can actually point at an actual covalent bond. So we can say that when we break up methane in a chemical reaction, we would be breaking 4 moles of CH bonds to do that. We don't do that with lattice enthalpy. Lattice enthalpy is very much just like a mole of lattice, so a mole of sodium chloride, for example. And if it's association, which it almost always is, because you're making bonds between the ions, it's exothermic. If you are doing an A-level syllabus that talks about dissociation, lattice enthalpy of dissociation would be endothermic. Or if you're doing something like a Born-Haber cycle or some other calculation where you want to switch the arrows going up, so when you're, for example, breaking ionic bonds, that's when you need to put a positive sign on it because you're breaking bonds. It's endothermic. Okay, still on the kind of Born-Haber cycle theme, there are 2 other things that happen when we make an ionic compound. So before we can even bring ions together, we have to make ions. And we make ions either by ionization energy, removing electrons, or electron affinity, adding electrons. So they are opposite processes. First, ionization energy, very important definition. Energy required to remove the outer electron from each atom in a mole of gaseous atoms. And electron affinity is the energy change when an electron is added to each atom in a mole of gaseous atoms. So although they're not technically bond making or breaking, they do refer to processes that have to either overcome attractions or bring 2 attracted species together, because there is always an attraction between the nucleus and the electron. We're normally talking about outer electrons in this instance. Also, because we're talking about these individual processes rather than an overall chemical reaction, everything is happening in a gas state. So for first ionization energy, I need to have my sodium atoms as a gas before I can remove electrons from them, because as a solid, the electrons are all delocalized. They're not going to be removed. Similarly, if I wanted, for example, to add an electron to fluorine, I need it to be gaseous atoms, not fluorine molecules. I need to break those bonds so that I've got individual fluorine atoms, because otherwise I can't add an electron if there's a covalent bond already using that electron up. And so first ionization energy, or in fact any ionization energy, is always endothermic. We always have to put energy in. We are overcoming attractions between the nucleus and the electron that we're removing. So there will be different sizes of ionization energy, and we may say, for example, that sodium has a relatively low first ionization energy, but it still has energy that we need to put in to remove the electron. Whereas electron affinity, the first electron affinity is exothermic. You're adding an electron to an atom, and the electron is attracted to the nucleus. So you are bringing together 2 things that are attractive. However, when we add the second electron, for example, if we had an oxide ion with a minus charge, and then we added the second electron to make our what we think of as an oxide ion, an O2 minus, that process will be endothermic, because I'm now trying to add an electron to a negatively charged ion, and we need energy in there to overcome the repulsion between 2 negatively charged species. Okay, before we can do ionization or electron affinity, we have to atomize our elements. The only elements that exist as single atoms are the noble gases. they're not really going to be doing much in the way of, for example, making an ionic compound. And so therefore, in our Born-Haber cycles and everything else, we need to atomize elements before we can remove electrons or add electrons to them. And so the enthalpy of atomization is per 1 mole of gaseous atoms. So we are talking about making 1 mole of the product rather than taking 1 mole of element. It's always endothermic because I am always breaking bonds, and the type of bond that I break depends on what sort of element I'm starting with, a metal or a non-metal. So if I start with a metal, for example sodium, what we mean when we say that sodium solid turns to sodium gas, that atomization, because there's no change in the formula, so it doesn't really look like much is going on, what we're doing is breaking all of those metallic bonds in that metallic lattice of ions and delocalized electrons so that we get individual metal atoms formed. When we take a non-metal, for example oxygen, we're taking half a mole of oxygen gas because it's per mole of atoms. So I need to make single atoms as my product. So even though it starts as a gas, there is a chemical change happening. I am breaking that double oxygen bond in between. Or for hydrogen, I would be taking half a mole of H2 and I'd be producing 1 mole of hydrogen atoms. So there is a link for covalently bonded diatomic elements that actually the enthalpy of atomization, so delta H atomization, is equal to half of the bond enthalpy or mean bond enthalpy for that element. So if I take half a mole of O2 molecules, I'm breaking half a mole of those bonds and I'm producing 1 whole mole of the individual atoms. All of this is happening not in a gas state, but we are always the product in a gas state. So we may not start in a gas state. If, for example, I was taking iodine, I would have to turn it from a solid to a gas first. So there's a bit of energy required to do that, then break the bonds between the iodine atoms in a molecule. The last enthalpy change we're going to look at, which is an individual process, is hydration enthalpy, which if you haven't done that yet, it's going to come up in the topic about solutions and enthalpy changes. So this again is an individual process. It is not the same as solution. So if I was doing enthalpy of solution, it's an overall chemical reaction. I can make a solution by simply taking a solid like sodium chloride and putting it in water. I can stick a thermometer in and I can measure the overall enthalpy change. Hydration is an individual process that occurs during that reaction. So hydration is when we take a mole of individual type of ion like sodium or chloride in a gas state and then they get surrounded by water. So it's measuring, like lattice enthalpy, simply the strength of the bonds. So lattice enthalpy is taking the gaseous ions, and they come together and they make ionic bonds. This is taking the gaseous ions and adding them to water, and they make attractions between the ions and the water molecules. So because we're forming attractions, then this is also an exothermic process. So it's not traditional bonds. We're not making ionic covalent or metallic bonds. But what we're doing is making something called ion dipole attractions, and these ions are known as hydrated ions. So for example, the oxygen in the water points towards the positive ions, and the hydrogen in the water molecule will point towards the chloride ions, and there are attractions that are formed. Hydration is measuring therefore like that strength of attraction. It's the energy out that determines quite often how soluble something is compared to the energy in, which is the lattice enthalpy.